let's go and get started. Couple things. Let me get the sign-in sheet passed around, or I am going to forget it. Okay. I went ahead and laid out some handouts up here for those of you that are in concrete design. If you're not in concrete design and you grabbed these, like put them back. These are just for the concrete folks. Let's talk about steel though. So you have a homework due today. So there's a pile over here on this side of the room that we are that I'm currently collecting work for. Here you go. Homework 5 is going to be assigned on Friday, so you give a little bit of a respite. And I'll tell you, homework 5 is going to be pretty short. Welded connections you're going to find is not very difficult. It is what it is. So I'm going to assign that on Friday. It's really probably only going to have 2 problems on it, and it's going to be due, I think, the following week. And then I think about all the homework that we have that's due before spring break. So your second exam, though, will be before spring break, and it will be on bolted connections, homework 4, and welded connections, homework 5. So that'll be exam 2. Yes? What? Remember, we're going to review on Monday, exam on Wednesday, and then that Friday we're canceling class. Yeah, is that I just okay, that sounds right. So the exam's on the 15th. Sound good? So, in fact, why don't I go ahead and pull the schedule up on the syllabus just so everybody's clear. If the computer would decide to cooperate. Oh my goodness. Okay, so we are right here. So it's the 19th. We're doing welded connections. It seems like we're a little behind, but we're actually going to probably make up some steam today on welded connections today. We will assign homework 5 on Friday, and we'll probably be beginning columns on Friday, get into columns between now and spring break. Monday we have our exam review. Wednesday we have the exam. And then Friday before spring break is a makeup day. Assuming we don't have a blizzard between now and then, we'll go ahead and cancel class. Sound good? All right. What's that? The makeup day, yes. No problem. All right. Then let's get into welds. I do want to sort of make up some ground today. So, what? Oh, well, thank you. Well, thank you. Okay. No, I'm good. Oh, God. This is showing up on the recording there. Oh, God. Oh. I'll think about it. I'll think about it. There's something to that. All right. For my birthday, we'll talk about fillet welds. How's that? Okay. So last time, if you recall, we talked about weld metal capacity and base metal capacity. And if you recall, weld metal capacity is a function really of the effective throat, the dimensions of the weld, and your electrode strength. Beyond that, it's very plug and chug. Base metal capacity is very similar. Just a function of your steel grade and your gross and net area. I mean, it's pretty simple. We were in a little bit of a hurry on the weld limitations. Thought I would just sort of briefly go over those again. Just like with bolted connections, there are limits associated with welded connections. Now we have, for welded connections, we have minimum and maximum weld sizes, and they are for very specific reasons. Now minimum weld sizes if you recall, the reason for that is the heat sink effect. I mean, if you've got, and I know the example was a little out there, but if you've got something like an 8-inch thick plate and you're trying to place a bead of weld that's only a 1/4 of an inch in size, well, that super thick plate is going to act like a heat sink, and you're not going to get the weld penetration that you need to fully develop that joint. So you're going to get a very brittle joint, and you're not going to get an effective weld. So based on the material thickness of the thinner part, so if you have a 1/2-inch plate and a 3/8 inch thick plate and you're welding those together, you go off of the 3/8, since the heat sink effect, you're trying to be conservative, going off the minimum thickness. Based on where you're at, you can determine a minimum size of your fillet weld. Okay, so that's pretty straightforward. That's the one that you look up. Okay, now for maximum, and again, this goes into rapid cooling, just as I was mentioned earlier. That's minimum sizes. Maximum size of a weld is either the thickness of the plate or the thickness of the plate minus a 1/16 of an inch, depending upon how thick your plate is. If your plate is less than a 1/4 of an inch thick, we just say, what the heck, let's just let the weld equal the plate thickness. If not, thickness minus 1/16. And the reason why is really because of this right here on the right. Our thought is, if you're placing a fillet weld, we'd like to maintain the geometry of the plate, so we sort of back off the maximum weld size about a 1/16 of an inch, because if that weld gets too big, what's going to happen is you're going to start to melt this part of the plate right here, and then you're not going to have a really well-defined edge for placing your weld. Now that's for pretty typical plates. For really thin ones, stuff that's like a 1/4 of an inch, we say, what the hell, go ahead and melt it. It's small enough anyways, it's not really going to matter. Sound good? So, let's, just so everybody's clear, we have minimum and maximum weld limits. The minimum limits are for rapid cooling and for that heat sink effect. We need a stout enough weld to penetrate through the plate and actually develop a proper joint. The maximum weld size limit is intended to maintain the geometry of the plate. Right. Sound good? There are also limits on weld length. For instance, the minimum length of a weld that you can count on for structural capacity is 4A, where A is how big the weld is. So if you have that weld has to be at least 2 inches long for you to count it for structural capacity. I'll be honest, we really don't run into that. That's usually not a big issue from a design standpoint. And in most building connections, we don't even get close to this stuff. If the weld gets too long, we apply a reduction factor for its capacity, but too long, I mean, you're talking about really, really long welds. Most of the welds that we look at are well within these two limits, and it's really not a big concern. So far, so good? Yes?
What did you say A was?
Okay, that's a good question. A is, instead of drawing it, A is this. A is when we say the size of the weld, I'm referring to the leg of that triangle. The throat is 0.707 times that. It's a good question. Sound good? All right. The only other thing that I think is really worth mentioning is not really anything that you're going to find in the spec. Well, first off, let me put this. So I have a summary of slides. It starts on 246. It goes from 246 to 247. And those are just a summary of all of the weld equations. So it's definitely something you want to put a big star in your notes, because literally it's all right there. We have the weld metal capacity and the two equations for base metal capacity, either shear yielding or shear fracture. And then we've got weld limits, minimum weld sizes and maximum weld sizes. All right. So if you haven't already put a big star on that, you definitely have to. Sound good? Okay. This one right here is not something you're going to find in the code, but it's definitely something you're going to want to keep in the back of your head. By and large, a very, very common weld size that we use for design when possible is 5/16. And where the heck are you coming up with 5/16? Okay? 5/16 is about the largest weld size that we can deposit with a single pass. Okay? So let's to explain that, let's say we've got something like a 3/4 inch weld, like some really, really big weld that we've got to deposit. Maybe it's the column base plate on a 50-story or something, a nuts weld. Well, in order to deposit that weld, you have to make multiple passes of your electrode. So you might have something like this. Let's see, you got this, you got this, you got this. Okay, let's say you're trying to make this connection. Let's say you need something like 3/4. So you're going to make a pass. So let's be clear, the plate goes in and out of the screen like this. So you're going to pass the electrode along this joint. You might place a little bit of weld material, and it might look something like that. Okay. Well, in order to get that really large weld size, you've got to make multiple passes. So you're sort of taking that weld and you're building up on it. So you might have another pass that sort of does that, and then you might have another pass that does this, and so on and so forth. And you're sort of building up on it. So you might have one that sort of, does that. And you might have another one like this, and you have another one, like that. Everybody see the kind of idea? You've got to make multiple passes to get those really, really large weld deposits. Now, in a single pass, just about the largest weld size you can get is 5/16 of an inch. Okay? And more often than not, if I had the choice between using a 5/16, let's put it like this. If I had a choice between a 5/16 inch weld or a 3/16 inch weld, I'm going to go with the 5/16 any day of the week, because a larger weld size is going to result in a shorter weld length. Okay? And typically a shorter weld length is quicker to deposit. Okay? So faster weld means less labor, less time, less money. Okay? All right? Ultimately, as long as you're getting the same effective area of the weld, bless you, as long as you're getting the same, effective throat multiplied by the effective length, as long as the area is the same, you could have a short 5/16 inch weld and a long 3/16 inch weld, and they both have the same capacity. But from a fabrication standpoint, what's going to be quicker and easier to deposit? The larger weld size, shorter weld length. Does that make sense? Yes.
So would a shorter weld length also reduce the possibility for defects in the weld? Like the longer a weld you have, the more...
That's a good point, and I'd say, I don't want to say yes, but most likely. When you weld, you are introducing a flaw. Like that's what you're doing, and there's the potential for microcrack to develop. Potential for loss in ductility. That's what you do when you weld. So anytime that you weld, especially high capacity structural welds, along with that comes a high degree of QA/QC, a high degree of weld inspection. Just from that standpoint, fewer welds means less inspection, less QA/QC. So you're right. But I don't want to say that the answer is always yes. It's most likely, I'd say. That's a good question. Anything else? This is good stuff. Yes, sir.
Kind of like what you said, though. What's the trade-off for putting multiple welds in one spot?
What do you mean?
Like if you're doing that to increase the straight, what's decreasing?
Are you talking about this?
Yeah.
I think you're looking at it a little bit in a little bit of an incorrect fashion. What I'm getting at with this is that, this particular connection, this particular example I'm talking about a column on a 50-story building. You've got to have a weld that big. You see what I mean? There's really no ifs, ands, or buts about it. So there's no real trade-off. What's up?
What do you get nighttime outside?
Oh, we're supposed to get hit with some serious rain, which I have to actually end concrete a little early because I have a meeting at 11 o'clock in Corbley. So, yeah. I bought an umbrella this morning. I'll just Mary Poppins across. Oh goodness. All right. So any other questions before we get it? Did that sort of answer your question? We're talking. There's really no way to get around that on a weld like this. I mean, you just have to sit there and keep passing and passing until you reach your appropriate size. I'm saying when you have the option.
Well, when you do have that option, would it be better to weld or to mold?
It depends. There is no look. There is no simple yes or no answer. Let me put it like this. So let's say you are doing a beam-to-beam connection in a building. So a typical floor beam connecting into a floor girder. A very common connection is to use clip angles. And in that instance, you're probably going to see just bolting. You know, have a beam framing into another beam. So you've got a clip angle, bolts through here and bolts through here. So that there's no welding. But another common connection is to have an end plate pre-welded onto that beam with holes in it, and then you just erect in, bolt, and you're done. It's not as simple as saying, well, one's always cheaper than the other. It depends on steel prices, depends on labor rates. There's no yes or no answer. I'd love for there to be, but there isn't. So it's just project dependent, price dependent. You just need to be able to do both. All right, two questions. It doesn't matter. What's that? Well, that's going to be one of the issues in design. We're going to select the weld length based on limitations. Oh, yeah. We're more often than not assuming 45-degree angles. Rarely are you going to have like one weld leg that's way larger than the other. In fact, I don't think I've ever encountered one in a design capacity. We've always assumed 45, 45, 90, so that they're the same size. It's a good question, and it is possible to deposit it that way, but
But you don't ever do it on purpose.
no.
So I know as an engineer, we try and keep things as economical as possible, but say we don't care for some reason, like us personally, about welds or like are those laid out for us beforehand, or do we have to look at ourselves?
Well,
What would work better for the
I'm trying to come up with a simple answer to your question because it's not. I get what you're saying, and it's not a simple question to address. What I'll say is this: there are hundreds of ways to do very basic connections in a building. Okay, you can use clip angles and never use a weld at all. You can have, just as an example, or you can have plates pre-welded onto the end of a beam, and then when you bring it into the field, just set it in, bolt, and you're done. Which one you use, I mean, yes, it is a function of labor prices and steel prices and all of that, but it's also a function just generally of your fabricator. I mean, if your fabricator has their automation and their process set up to do welding a lot easier than another fabricator, they're probably going to do a little bit more welding. Fabricator over here might be doing a little bit more bolting. There isn't really a simple answer. I mean, it's project dependent. There are some connections, I would say, where you can't get around. I mean, you got to have some welds. Like if you're doing a flange to web connection on a plate girder, that's a weld. There's no ifs, ands, or buts about that. Does that kind of make sense?
Wouldn't like the architect or like the client have something with that as well? Like what you use depending on
In a building?
Yeah.
Oh, the client doesn't care if the building's made out of steel, concrete, popsicle sticks. They don't care. No, I'm serious. They don't care. I mean, they just want a building that stands up. All the architect cares about is that ingress, egress requirements are met. The clients, bless you, all the codes are met for building size and lighting and all that. That the project meets the demands of the client, in terms of square footage and all that. That it looks good. But by and large, as long as we're fitting within the architect's and the client's constraints, that's on us. We can do what we want. Does that kind of make sense? Yeah, the client, they don't care if the building's made out of steel or popsicle sticks. They don't care. I mean, think, if Geico Insurance needs a new corporate headquarters, and they contact Lewis Engineering, and Lewis Engineering is going to design the frame for them, you think the Gecko cares whether or not their bolts or welds?
Nobody wants to save 15%.
He does. The Gecko does want to save 15% or more, but That is a fantastic question. I'd say you glue them. You glue them.
Catch on fire. You're like, all right, final weld.
All right. Any other questions?
You were talking about the Fillet. Are those made out of like stronger steel since they're smaller?
No, they're usually actually made of weaker steel. I mean, angles are typically A36. They just might be thicker. So the big thing is just to make sure that you're match drilling so that the holes line up. And as long as you've got block shear, oh wow, it's coming down. All right, all right. Any other questions so we can get into some welded connections?
You're not getting your meeting.
No, I have to go. There's no ifs, ands, or buts about that. All right. So let's look at this. So I want to determine the strength of this connection shown. So if you notice, are those welds longitudinal or are they transverse? They're going along the direction of the load. And if you ever design a connection and you have only transverse welds and I find out about it, I'm going to have you stick your hand up. I'm going to go, no, don't do that. So longitudinal welds only. All right. Goodness. Now I've got a plate that's 10 inches by 3/4 of an inch. Now my weld, help me out. What's the size of this weld? It's a 5/16 inch weld. How long are they? 15. That's what these two numbers mean. Remember, 5/16 and 15. The triangle indicates that it is, in fact, a fillet weld. Okay? So as long as you understand that terminology, I'm good.
Since it's on both sides, isn't it supposed to be like a triangle on the top?
True, but you can also get around that by just pointing at both of them.
Okay.
Yeah. And on long plate connections like that, I tend to do that more often than not. Sound good? All right. So I want to determine the strength of the connection, the design strength. So we've got A572 grade 50 steel for this tension member. We have E70 electrodes. So the electrode strength for these welds is 70 KSI. It's pretty simple. All right. So let's take this one at a time. We've got the weld metal capacity and the base metal capacity. It would help if I had my example problems opened. No, it's not. You'll know one way or the other, I'll tell you. What? Does that sound like something I would do? Oh, your faith in me is staggering. Oh, God. This is recording. You realize that, right? Okay, all right, let's get back on track. All right, so here's how we're going to handle this. We're going to take each capacity one at a time. So we have weld metal capacity and we have base metal capacity. So let's start off with the weld metal capacity. I'm telling you, this is really simple. So weld metal capacity. Okay, first off, we have E70 electrodes, so our electrode strength is 70 KSI. Okay, that's number one. All right, number two, we have a weld that has a leg size of 5/16 of an inch. Okay, and what I'm going to do for the length of the weld is I'm going to say it's 2 FE. Oh, hold on, it's FEXX.
What does that mean?
Just electrode strength. Because think about it like this. We have FE70. So that's it. Yeah. Yeah. So. Okay. All right. What I'm going to do for the weld length is I'm going to say that the weld length is 30 inches because it's 2 times 15. All right. Pretty basic, right? So here's the weld metal capacity. It's this simple. So phi Rn is phi. Now what is phi? I'm just curious. It is. It's on the, see, I've got those summary slides. So, oh goodness. Oh, wow.
No, not at all.
I mean, here it is. It's pretty straightforward. We have 0.75 for phi. We have our nominal capacity of the weld is 0.6 times the electrode strength. Remember that whole von Mises, 0.6 times the capacity, because we're assuming that the weld is resisting the load and shear. And we have 0.707 A times the weld length. Now, that's it. So plug and chug. So 0.75, 0.6, 70 KSI, 0.707, 5/16, and 30 inches. And then we get phi, so 208.8. I have a second on that?
Yep.
It's that simple. That's not that bad, is it? It's horrible. What? An exam on Friday? What? I'm just going to focus on base metal capacity. All right, base metal capacity. All right, so to do base metal capacity, we have shear yielding and we have shear fracture. But a couple things we need to get out of the way right now. So we have a weld length of 30 inches. Now, what is the plate thickness? Because now we're looking at the plate. We're not looking at the weld. 3/4. Okay. Now, let's start off with our areas. Okay, so we have gross area and net area. So let's start off with the gross area. So gross area in shear. Okay. Now, gross area in shear, when we did block shear, I mean, how did we figure that out? It was the length in shear times the thickness. Well, since the length of the weld is 30 inches and the thickness is 3/4, the gross area in shear is 30 times 3/4. But before I start doing anything, let's also look at the net area. In general, how do you compute net area? You take the gross area and you subtract the area lost due to the presence of bolts. There's no bolts. So gross area equals the net area. So therefore, gross area in shear equals the net area in shear, which is, oh, that made no sense, LWT. So 30 inches, 3/4, which is 22.5 square inches.
I mean, but unless you're at the case where you have like we were talking earlier, where you would have like a beam and a face plate in a W shape. In an instance like this, you're going to use bolts, correct?
Okay, hold on.
Do you understand what I'm saying?
Not.
Like, how are you going to bolt? No,
Hold on. You're
connection like this, like your girder and a beam. I know you can't do that.
you're testing my 3D art skills, but let me try something. All right.
Maybe I'm.
No. You're making a reasonable point. Let me try. Okay. Give me a chance. All right. So don't draw anything out because I gotta fix a couple things. All right. So we've got this and this. All right. Now the first thing that I propose that we do is we cope that off a little bit. So it's going to be kind of like this. This is not turning out exactly the way I wanted it, but something like that, right? That's about the best you're going to get. No, hold on, let me finish. Now, you're going to have a plate right here and a plate right here, and you might have, bolts right there that bolted into whatever it's being attached to. What I'm saying is that plate might be affixed to that web with welds there and there. It's a happy little weld. Okay. Now, in order to calculate base metal capacity, there's something else that we're going to need for the base metal. You tell me. Or two other properties we're going to need.
FU value.
There we go. Fy and Fu. So what is the grade for this plate? What is it? A572 grade 50. And for A572 grade 50, what's the Fy and the Fu value?
50 KSI, 65 KSI.
There we go. Is everybody able to find that? And then that's because we have A572 grade 50, table 2-4. All right. Sound good? So in order to appropriately handle this connection, we're going to do shear yielding and we're going to do shear fracture. Now, to compute shear yielding, help me out. What's the phi value? 1. So for shear yielding, our capacity is 1 times 0.6 FYAG, right? AGV. So phi RN, and maybe I'll do this. Phi RN Y is 0.6 FYAGV, which is 1 times 0.6 times 50 KSI times 22.5 square inches. So that's yielding. Now phi RN for fracture is, now what's the phi for fracture? 0.75. So 0.75, 0.60 FU A N V. So 0.75, 0.6, 65 KSI, and 22.5. So what do we get for the top one?
675.
675.0. I got a second on that? And what do we get for the bottom one? So on your homework, you were doing problems where you were getting, like a load of 200 kips and you were getting a bearing capacity of 500 kips. That's fine, okay? All that means is if I take this connection and yank on it, like in this instance, it's the same story. We've got a weld metal capacity of 208 kips, but we have a base metal capacity of 675 or something. But if you yank on this connection, the first thing that's going to happen is the weld's going to fail, okay? And think about it. You have a 3/4 inch plate and you have a weld that's only 5/16 of an inch. I mean, shouldn't be that surprising, right? Sound good? So the capacity of this connection is 208.8 kips. So if you want for the connection VRN is that. Now, one thing I do want to mention, if you go through and actually do the math for gross section yielding and net section fracture, I mean, you do still have a piece of steel that you're yanking on, you'll find that for this connection, gross section yielding is about 338 kips, and net section fracture is only 318.1. So, or 318.1. So 337.5 and 318.1, this still governs. Okay? So.
But before we had good, section yielding, is that really the net section fracture for the area with the bolts? But now
There's no bolts.
there's no bolts, so it's just fracture across the beam in general, or what?
Well, okay, so a couple things. Number one, the net area equals the gross area, just like it does here. Okay? The only thing that's worth some additional discussion is the shear lag factor. And if you turn to the shear lag table and you look at the shear lag table and look at case 4, p-value, yes. Go to case 4 and you'll see what I mean. This is one we didn't do before because we really weren't interested in welds. Whew, that looks bad. Yeah, so you would determine your shear lag factor as a function of the length of the weld versus the width of the plate. And whatever that ratio is would determine what your U value is. But other than that, that's the only difference. The net area equals the gross area because there's no loss in area due to the presence of bolts. Does that sort of help answer your question?
I always looked at it sort of like, which is going to happen first, fracture, because the bolt holes are yielding just in general. And now it's like, well, yielding is going to happen first.
Well, I propose neither of those are going to happen first. What's going to happen first is this.
Oh, okay. Yeah,
Right here. Now, hold on.
I'm saying that if that was, we calculated that was a really big capacity, then of course yielding's going to happen like that.
Not necessarily. Depending upon the numbers and the grade of steel, you could have fracture at that connection before yielding out in the main body. Remember, it's not yielding and fracture in the same place. Okay, so that's possible. I'd say that for welded connections, you're on to something that it's more likely, but it's not always the case.
Why would fracture happen at the connection? Well, I guess.
Because of shear lag. Because remember, shear lag is accounting for the fact that not all of that area right there around the connection is effective in resisting the load because the stresses aren't uniform. You're probably still thinking, oh, well, the stresses are all uniform, so it's just, since Fy is smaller than Fu or Fy is going to happen first. But it's not just the yield stresses, it's also the areas. You see what I mean? Does that make sense? Like if I have if I have a normal piece of steel and I'm, yanking on it, but I have a really high quality grade of steel and yanking on it, if they're the same size, well then the regular steel is going to fail first. But if I've got a really big piece of normal steel and a really tiny piece of very high quality steel, well, it's not so simple. You see what I mean? Does that kind of help answer your question?
That kind of comes with experience, doesn't it?
No, I'd say no. I think it comes with just doing the math.
Material properties, so like,
Well,
in the homework, I know like the plate was 836. And
well, knowing the material properties comes into practice. Well, no.
I know we're not using traverse welds by themselves, but if you were to add a traverse weld because they're going bigger welds, would it raise the stress enough to be effective? Or
Yeah, it would. You're absolutely right. More weld equals more capacity. I mean, it's,
how much of a traverse weld?
It depends on however much you add. I mean, if you add another inch of weld, that's another inch of LW. That was simple.
So it's not analyzed separately?
It can be, but conservatively it's not. The only time you actually ever specifically handle weld orientation is if you have an eccentrically loaded connection, but that's a whole nother animal. No, go ahead.
Those welds being loaded longitudinally, and then if you were to add a transverse weld, it's tension instead of shear force.
Yeah, and that goes back to those curves that we were looking at earlier. Technically, transverse welds can hold up more load, but they're less ductile. Typically, what is done is we just, you know what, they're all resisting the load through shear and they're all behaving the same. You're going to get a conservative answer anyways. But the big point is don't use the transverse welds by themselves. I mean, transverse welds are fine if there's longitudinal welds also. Does that sound good? Anybody else? All right. I do want to look at something else real quick, and I want to look at the weld limits. Okay. So does everybody have this? I know that wasn't really part of the example, but I think it's important. Okay, so weld limits. Okay, so we have a weld size that's what, 5/16? So I want to check the minimum and maximum weld size. Let's take the minimum. How do I determine what is the minimum weld size? No, that's maximum. Well, you need plate thickness either way, but my point is there's a formula for maximum. For minimum, there's the table, yeah. So let's find that table. I'm making you all go through your notes. Oh, no. Well, yeah, but I want you to find it in the manual, too. But I want you to be able to find it in the manual. Now, it's table J2.4. It's on 16.1 dash what? 111. All right. So we have a plate. What's the thickness of the plate? 3/4. So over 1/2 to 3/4, we have a minimum weld size of 1/4 of an inch. Okay. Now, that's our minimum weld size. So we'll put a min is 1/4 of an inch, and I got that from that. Now, A max. Okay. A max is either the thickness or the thickness minus the 1/16 of an inch, depending upon whether our thickness is less than or greater to 1/4 of an inch, which is much larger than that. So our A max is T minus the 1/16 of an inch. So that is 3/4 minus 1/16. So 3/4 is 12/16, so that's 11/16. And we have an A of 5/16. Sound good? Everybody all right with that? So our A is 5/16, so we are okay. Any questions? This isn't so bad, is it? It's pretty simple. All right, if you understand that, does everybody have everything on the screen? Everybody good? All right. Okay, well, if you understand that, then the design of a fillet weld is pretty simple. When we designed bolted connections, I mean, how did we go about it? We said we've got the capacity of a bolt, we got the load, divide to get the number of bolts. Well, Well, for welds, it's you got the load, get the capacity of 1 inch of weld, divide to determine the number of inches. That's it. It's really that simple. We use the weld limitations to determine the appropriate weld size. When in doubt, we want our weld size to be as big as possible as long as it doesn't go over 5/16. Okay. Now, if we're talking about a crazy connection where we've got to use a 3/4 inch weld, well then use a 3/4 inch weld. But most typical connections in straightforward structure, you're going to want to keep it 5/16. You might have to go under that if your limits don't allow you to get if you have a maximum weld size of, let's say, 1/4 of an inch. But when in doubt, go to 5/16. All right. Determine the capacity of 1 inch of weld. Divide to get the total number of inches. That's it. So we're going to do a very similar example, only in this instance we are in design mode. So now we've got, yeah.
The 5/16 inch, that's just a number to know that's defined by
No, that's not defined by code. That's one of the, that's just, yeah, that's just about the largest weld you can get in a single pass. Now, if the numbers don't work out right and you do a design and you've got a weld that's 80 inches long, well, use multiple passes to get it shorter. Right. Sound good? All right. So using E70 electrodes, let's design a fillet weld to resist a service dead load of 15 kips and a service live load of 40 kips. I guess I should put that the live load's already reduced, but I mean, I think we pretty well recognize, unless it says otherwise, the live loads are reduced. We got a similar grade of steel, and we assume that the capacity of the gusset plate is adequate. In other words, when we check our weld or base metal capacity, we can just worry about this one. We don't have to worry about that. Sound good? All right. This is what we're going to do. Next time, I want to get through this example, and I want to try and get through this one pretty expeditiously, because our last weld arrangement example is looking at a balanced weld. And I do want to at least introduce what that concept means. So if you look at the configuration, let's put it like this. Here's example 13. We're going to do it real quick, and we're going to get this answer, okay? And I'll show you how we get that, next time. But let's take a look at this. This is a rectangular plate, okay? Just a plate. And we're going to determine that we need about 12 inches of weld, okay? So just based on common sense, doesn't it make sense if you were laying out this connection, put 6 inches of weld up here, 6 inches of weld down here. Sounds simple, right? Okay. Now that's easy for a plate, okay? My question is, what if it's an angle, okay? If it's an angle, you might not want to do that, okay? And the reason why is because the centroid for an angle is offset. The centroid of an angle is actually closer to this side than it is to this side. So we're also going to do a welded connection design problem like this, and what we're going to find is we're probably going to have a connection that winds up something like this. We're going to have, like a lot of weld down here, but we might only have something like that up there, okay? And the reason why is because the centroid for an angle is closer to this end than it is to that end, so you put more weld here to resist that load than you do here. It's kind of like beam reactions. I mean, imagine if you had a beam right here and the load was all the way over here. Well, this reaction is going to be larger than that one, right? So you need more weld over here than you do over there. Literally the same idea, okay? And that concept is called a balanced connection. Right. Yes?
So would it be ideal to put a transverse weld directly at the centroid?
That's a good question. You can put a weld right here and account for that during your equilibrium, and we're actually going to do that for this example. We're going to put a transverse weld like this. It's actually a little more difficult to do a transverse weld. Like once you understand how to do that, you can do one without a transverse weld by just setting that capacity equal to 0. Does that make sense? All right, next time all right, hold on. Next time let's try to power through these weld examples because I want you all to be prepared for your homework. I mean, I'm giving you your homework on Friday, so I want you all to be ready for it. And then we begin, after welds, the topics in this class are going to take a complete 180 because up until now, we've been talking about fracture and yielding and things like that. Well, with columns and beams, we have buckling to talk about, and it's a completely different story. So things change after welds. I just want to give you a heads up.
Are welds going to be on the celebration?
Yes. No. That's the final. All right. Anything else? All right. If you're not in concrete, I will see you. If so, I'll see you in a few minutes.